All right, so we're going to pick up from the last lecture where we were talking about carboxylic acids, and now we're going to move over to nitriles. And we're going to see that nitriles, in a sense, have a very similar reactivity to carboxylic acids. And you can look at this by analyzing the sort of partial charges. So you see that the carbon of the nitrile has that partial positive charge, just like when we were to look at, say, a carboxylic acid. We see that we, of course, have that partial positive charge on the carbonyl carbon. Right? And so we can see that in both cases here, again, the nucleophile is going to add to where the carbonyl carbon is or the nitrile carbon. So basically here, both different carbons here are electrophilic in nature because of their partial positive charge. And nucleophiles add to nitriles at the nitrile carbon. So now that we can see how they kind of react in a way that's similar to what we've seen before, now we're going to look at basically how we can make nitriles. And the first one that we're going to talk about is, of course, one that you've already seen before. We've discussed this reaction before as well, and this is using an SN2 reaction to use the cyanide anion to attack a primary alkyl halide. You typically want to keep this, again, just to remind you that this is an SN2 reaction, so you're going to want to keep your alkyl halide primary. Sometimes you can get away with secondary, but primary is really the one that's going to work. So as an example, you can see that we have this sort of SN2 attack, and you end up with your nitrile that's added to that. Now, what I want to draw your attention to is that you want to be careful. Don't forget that you're adding a carbon or extending the carbon chain by one carbon there. Right, so don't forget about that. Sometimes those are some mistakes that can be made. So always remember that in this case you're adding a carbon there. Now, we're going to look at another method to make a nitrile, and this is basically by the dehydration of a amide. And so we're going to use thionyl chloride or SOCl2 and the amide. And so the whole sort of principle behind this is that we're going to make the oxygen of the amide into a good leaving group, right? So typically what we're going to do is treat this with thionyl chloride in benzene at about 80 degrees Celsius. So that's going to be basically refluxing benzene here. And you can see that we end up getting our nitrile as the product of this. So that's your sort of overall reaction that you see there. The other thing that I should note, though, is that you end up getting sulfur dioxide gas and 2 molar equivalents of HCl. And so there are two things that drive this reaction. One is, of course, the heat that we're using to force this to happen. And the other is that we're going to expel sulfur dioxide gas, which pushes the reaction towards the forward direction. So here is our amide that we'll use. And we're going to use our thionyl chloride here. And so I would venture for you to sort of pause for a second and identify the electrophile and nucleophile. Now, notice that we have our thionyl chloride. The other thing that's important to note is these electrons that are on the nitrogen are not available. They're in resonance with the carbonyl, so they're actually going to kick in, and it's the electrons from the oxygen that are going to go and do our attacking, right? So amide bonds have partial double bond character, and so remember that those electrons on the nitrogen are typically not available. So we're going to actually use the oxygen, and we get our first intermediate here. where we have the this sort of negative charge on our thionyl chloride portion. And note that now we have two of the three bonds necessary for the nitrile formation, right? Now these are going to kick back down and kick out the Cl minus, and again, don't forget that there's a positive charge on the nitrogen down there, which I'm going to go back and add here in just a minute. But you're kind of seeing now that we're converting that oxygen into something that has a good ability to become a leaving group. Right, so here at this point, we get our first equivalent of HCl by the Cl minus coming in and picking up that proton from the nitrogen. So that's number one, HCl. And then that, of course, gets rid of our positive charge and frees up some lone pairs on the nitrogen. So here is where I am going to kind of draw your attention again to what we just have formed, which is in effect a good leaving group. That's this guy, the whole piece, the OS double bond OCl. That is our leaving group there, right? So good leaving groups do what good leaving groups do, and they leave. And so we're going to kind of help it along by using the lone pair on the nitrogen to kind of kick in and boot that guy out of there. So now we're just going to kind of draw our next sort of piece that we see around there with it. And what we're going to notice is, of course, we pretty much have all of the nitrile formed. We have the pesky little proton that we've got to deal with there. And we'll take care of that guy in just a minute. And here we have our sort of leaving group that's going to decompose now into the sulfur dioxide, which is a gas which will bubble out of solution, driving the reaction. And here's our second equivalent of HCl. Now coming back to reform, I'll just push it down here, reform our nitrile. So now you can see here that this is the product that we form. And again, the whole sort of mechanism behind this is actually formation of a good leaving group. So let's kind of briefly pause for a minute and look at how nitriles react. We already kind of talked about this, but I'm just going to show you again in similar terms as with carbonyls. Notice that they undergo this addition here, right? That both of these behave in sort of the same way, in that we have addition at either the carbonyl carbon or, in nitrile's case, the nitrile carbon. Right, notice you see there that partial positive again, just like with the carbonyl, you see the partial positive on that. Our intermediates are very similar as well. We get, in this case though, for the nitrile, we get what's called an imine anion intermediate. Now, one of the things that we're going to kind of talk about coming up is that we can actually convert nitriles into many things. We can convert a nitrile to an amide. We can convert a nitrile then to a carboxylic acid by hydrolysis of the amide. So we have many possibilities. You can also convert it to an amine or to a ketone. So we can undergo hydrolysis of nitriles in two ways. And these can be either acid or these can be basic hydrolysis mechanisms. So I'm going to give you sort of the general reaction that we're going to use here. So we'll just say here that this is either acid And then you, of course, need some heat, or you can have base, also with heat, and you can convert this now to your carboxylic acid. Notice that the nitrile carbon is the carbon that has the carbonyl. So let's look at how this happens in the basic mechanism first, and then we'll review the acidic mechanism for hydrolysis. So here what we see is that, of course, we have a strong base, and it's going to attack the nitrile carbon because we have a partial positive charge on there, just like we've already seen before, right, in those in the previous slides. Right, so the question becomes, where does it attack? Well, we can see that, of course, from the previous slides, we can say that it will attack at the carbonyl carbon, or the nitrile carbon in this case, due to that partial positive charge. So we're going to kick this guy over, and we're going to get our first intermediate, which again we're going to see is going to be our imine anion as the intermediate. Now, we're going to have a little water left in solution, and so that's very quickly going to protonate the anionic intermediate that you see here. So we go back to the amine. Notice that in every case that we're going to regenerate this OH minus, right? We never have any species that's protonated with a charge on it. We are in, again, basic conditions. So now what's going to happen is we basically see here that we have our intermediate, and we have more of our OH minus. That's going to drive this process that now very quickly gives us back to the anion of the amine, which is going to, again, very quickly pick up another proton from water. Now the next few steps are important here, and we're going to need to analyze those kind of carefully. So I'm going to draw what we have, and I'm just going to kind of flip it over a little bit. And so now, again, we have this, we have an amide now, right? We're back to this sort of amide intermediate that we have here. And so, of course, with continued heat and base, we're going to attack the carbonyl carbon and push those electrons up. So we end up with this guy, and now we kind of end up with a little bit of a conundrum here, and we have this OH down here at the bottom. Now we're under strongly basic conditions, so we have a lot of base in solution, right? And so what's going to happen is that in order to drive this reaction forward, the base is going to come and deprotonate the OH that we have there. This is important because what's about to happen could not happen without this very special intermediate. Right? Just remember, like the Cannizzaro mechanism, we had this very special dianionic intermediate. I'm going to kind of highlight here for you. So again, when you're looking at this dianionic intermediate, you'll note that you cannot kick out just a plain O minus by itself, right? So the only thing that can possibly leave here is the nitrogen. Now, even though NH2 minus is a terrible leaving group, the really is no other situation or other way for this to go, so it will indeed kick that out. Now, as soon as it kicks that out, it's almost instantaneous or pretty much at the same time that you're going to see this NH2 minus very quickly pick up a proton from water. So basically, as it's getting kicked out, it's also grabbing this sort of proton here, regenerating our base. So it's important to remember that this only happens because we have that dianionic intermediate. And then at the end of the day, you treat this with acid to neutralize everything, and you go back to your carboxylic acid. Don't forget that you have to do that, right? Because you cannot have the carboxylic acid in basic solution. All right, so now we're going to move to the acid catalyzed mechanism. And I want you to kind of pay attention here to some of the differences. Remember with the base that the OH minus attacked the carbonyl carbon or the nitrile carbon. In this case, we're going to activate it. So it's something that you've seen before as well. We've kind of talked about these, where the electrons on the nitrile here are actually going to go and pick up an acidic proton. So that's going to put a positive charge there. And so we basically, just like with a carbonyl, we've activated it now. This allows for the weaker nucleophile, the electrons on the oxygen here, to come in and attack the nitrile carbon. Notice that, again, in the acid mechanism here, right, we do not have a buildup of any negative charges, right? We're under acid conditions, right? So we do not see any negative intermediates here, right? And so now this is going to go and remove our positive charge, regenerate our acid. And you see I have another lone pair here. And so now I've got more acid in solution. And I'm going to further protonate my amine. So now you see that I again have basically this sort of activated species, right? And so it's activated towards this carbon. And so these electrons can kick in and kick that guy out to get rid of that positive charge. And so now you can see here that basically at this point, I've got another activated species. Right now, this carbon is again activated towards attack by our weak nucleophile that can come in and add there. So now you're kind of starting to see the sort of formation of our carboxylic acid. And so we still have some more acid in solution, right? And so the next thing that happens, of course, is we've got those lone pairs, right? So again, remember, we're not leaving with any negative charges, right? So let's first go ahead and get rid of our protonated water that we have there attached to this species. Let's reform our acid. And now those electrons can come in and grab this. And basically what we've done at this point is we've converted the nitrogen now into a leaving group. Again, notice no negative charges. I really want you to compare the base mechanism to the acid mechanism here, right? Because I want you to see the difference in the intermediates and the charges and what has to happen for the nucleophile to attack. Now, these electrons kick down and we kick out our amine. Notice that we still need to regenerate our acid at the end, and so we're going to do that by having water come and pick up that proton that's still hanging to the top there of our carboxylic acid. And this will form our final carboxylic acid product here at the end. Okay, so the next thing is reduction of nitriles. We can reduce them to amines. So here's my nitrile, and we can use a strong reducing agent like LAH in ether. And then don't forget that at the end of the day, you need to add some acid to help work up the reaction. So you're going to see here that we end up with our amine in this case. We go all the way down to sort of the alkane amine there. So one thing I do want to note though, or draw your attention to, is notice that we have the amine, but look, this is the nitrile, right? The carbon that's there right next to it, those two atoms. So remember, we have two species that are part of the nitrile, right? The other thing is that sodium borohydride will not do this. It will not work at all for this reaction. However, if you wanted a second approach, if you had something that was acid sensitive or whatever, you could use hydrogen gas and, of course, palladium on carbon. It will work to reduce the nitrile as well. So now you have two ways that you've seen that you can reduce the nitrile. Right. The other thing that's kind of particular about nitriles is that we can actually treat them with Grignards, right? So just like we saw with carbonyls, right, that they can react with Grignards, so too can nitriles. But there's a sort of a bit of a difference here in how this is going to work. And what's going to happen is that we're going to treat this nitrile with a Grignard. So let's just put a generic Grignard up here. Of course, this is going to be done typically in ether. And then we're going to do an acidic workup. And so what we do is end up with a ketone. So make sure that you take note of this and that you sort of pay attention to this reaction because it's quite useful actually. Now, again, remember that a Grignard reaction is under strongly basic conditions, and so we're going to go through the sort of first intermediate that we talked about, which is the amine anion intermediate. So that's really going to be the result of the first step. Right, so let's look at how all of this works here, and let's go through and sort of investigate how our Grignard reagent is going to sort of alkylate this to give us also a ketone. So I'll just do methyl magnesium bromide as my sort of Grignard reagent. And so, of course, it's going to attack, just like with the base, the nitrile carbon. And there you can see right there is going to be your amine anion intermediate. Right, so once we get here we're going to now basically add our acid. So that we've basically, once all of the nitrile has been attacked by the Grignard, we are going to sort of pick up the proton and move to, in a sense, the kind of workup part of it, where we're going to quench everything and add acid. And this, in fact, is going to hydrolyze everything for us. All right, so now we've got more acid in solution. And the amine is going to get protonated further. Right, and so basically now you can also see at this point that um, something that should kind of be recognizable to you, and that, again, we're now switching from the base to acid, and so we've got this activated sort of imine ion that allows for the water nucleophile to come in and attack at that carbon. Now, the next step is, of course, going to be regenerating the acid here. And so now we've got our acid back. Of course, we never really lost it. We have lots of acid in solution, but this is sort of the process. And notice that now we have our amine, we have an OH, and we have our other side of this here. And so nitrogen is more basic than oxygen, the lone pairs. And so what's going to happen is the nitrogen is going to now pick up an extra proton. And so you're going to see that again, now the nitrogen itself is actually going to be a leaving group. I'm going to flip it over here. Put the nitrogen on the bottom. And so now we've got a positive nitrogen, and those lone pairs on the oxygen can now kick back in, and the driving force for this, of course, is forming that carbon-oxygen double bond. And this boots out your amine, in this case ammonia. And then, of course, water is going to come back, and it's going to pick up that last proton there, and you can see that we end up here with the ketone that we formed. So whatever is on the sort of the carbon that's on the Grignard, that is what's added to it. So, and then the nitrile carbon becomes the carbonyl. Now, in this case, what I want you to do is sort of pause the video and see if you can get through this on your own. Give it a shot. Try to kind of work through it. Make this product using a nitrile. See what happens. So, if you and then check and come back and see if you can see how you do. So here is our starting material, and what we're going to note in this case is that I'm looking at the product, and I see that, okay, the only part of my starting material is the benzene ring. The rest of this I've got to add, and so I can see right away that basically, since the carbonyl there was part of the nitrile, I can see that I need to start from something that comes with the nitrile that is basically on that second carbon out. So I need to add first a carbon to my ring, and we can do this by Friedel-Crafts. And now I need to put the nitrile on there. Remember that we need to do an SN2 reaction. So I'm going to brominate here via radical bromination. That's benzylic bromination, right? And now I can react this with potassium cyanide to do my SN2 reaction to stick the nitrile on there. And so once we get this, you can basically see that here we have everything we need now to just simply add a Grignard reagent to this to give us our ketone. So you just need to make the Grignard reagent, basically whatever else you need to stick on there. And then we're going to work this up with acid, and there you go. You can see that you have your product. So what I want you to do in these cases is actually kind of break it down and see where things are coming from, right? So that you can actually sort of do this piecewise. Now, we're going to look at some spectroscopy here, and the first one that I want to draw your attention to is IR spectroscopy. And so for carboxylic acids, of course, we have the carbonyl that you see there, close to 1700, right? The OH is also there, right? So what I want you to note, though, is that look at this OH peak. Compare that to another OH peak of just a regular alcohol. Do you see the difference? Right? Notice where that this one with the carboxylic acid is a lot more broad, right? And see the difference in the peak there, that if you look at the alcohol peak, right, what you're seeing is that it, in this case, we're looking at, this is coming closer to 3,500, whereas the sort of broad OH peak expands a larger region and actually kind of comes down and partly covers up some of our CHSP3, right? So, and then nitriles on the IR show up typically around 2250 or so, and they, if you notice, you see that peak that's right up here. That's the nitrile peak, and what you should note about that is that the peak itself is pretty sharp, right? Not very broad, and it's about medium intensity. And then the last little bit of spectroscopy here for carboxylic acids that I want to draw your attention to is really the biggest issue that we have with carboxylic acids is that they come in at about 12 on the NMR. So, and this is the biggest thing that we can kind of note here. I do want to make the point that even though they do show up at 12, it's highly concentration dependent. That proton is exchangeable. So if it exchanges with a deuterium, then you're not going to see that peak. So it really depends on your concentration that you have in your sample if you see that or not. All right, so the next thing that we're going to talk about, we've kind of finished our carboxylic acids, and now we're going to go to their derivatives. So things that are derived from carboxylic acids, and it turns out that they behave in a very specific way. And we're not going to talk about these two down here on the bottom, so all you're responsible for are the ones that are not crossed out. And what's going to happen is that we're going to introduce this new term called nucleophilic acyl substitution reactions, right? And so in this case, these derivatives are basically an acyl group, which is the R carbon double bond oxygen that's attached to this Y. And these basically behave not through addition, but through substitution. So they react different than typical carboxylic acids, and then in particular ketones and aldehydes. So here we have this, and so we can see that Y in this case, we're going to refer to that as a leaving group because that's what's going to happen. They're all going to react as a leaving group. Aldehydes and ketones, of course, remember, don't have that, and so they're going to undergo addition. And remember, the exception is the Cannizzaro reaction. So if we look at sort of the general reaction pathway that we see here for this, what we see is that we have some nucleophile that's going to come in, right, and it's going to attack the carbonyl carbon, and it is going to give us this tetrahedral intermediate. Now, here's the difference. In this case, where we would normally on the aldehyde and ketone would just protonate the oxygen and go along with our business, what we see now is that Y is actually there and it's a leaving group. So we're going to reform our carbonyl carbon. And now we have the nucleophile that's there plus our leaving group Y that is there. So Y can be things like, of course, a halogen, right? A alkoxide. It can even be a negatively charged amine, right? All kinds of things. And so basically, really what is going to drive this and what makes the reaction work the best is it really depends on two things. It depends on your nucleophile, and it also depends on your leaving group Y. So the nucleophile can be either negative or neutral, right? And so our sort of driving force really and how this goes depends on those two um, species. All right, so thanks for listening, and we'll pick up on Tuesday.